Well, very good. Well, thank you very much for allowing me to spend an hour with you today, or a little bit longer. I'm happy to stick around as long as possible. My name is Rick Smith, and I'm with a small company called Structural Services Incorporated. We're headquartered out of Dallas, but we're basically a bunch of decentralized individuals that just love concrete construction. You have to be an idiot to work here and not learn something. We surround ourselves with a lot of experts in our company. Wayne Walker is one on the far right of the screen, Jerry Holland next to him, myself, Eldon Tipping, the founder of our company back in 1988, Pat Harrison, who was with John Rohr General Contractors for a number of years in the Face Company, and then also Bob Simonelli and many, many other folks. Brian Birdwell down in the front row has 27 Golden Trowel Awards to his name. So the difference of what we do is we actually help design large industrial floor slabs and large industrial projects, but we also show up at every project site that we are involved with. So we have boots on the field out there that are working with the floor finishers and learning some of the difficulties that we have with some of our design recommendations, and also some of the problems that we have with other designs. So our clients are numerous. We do 200 million square feet of industrial floor slab design and construction a year, and yet we're a team of less than 20 people. So a lot of involvement there, a lot of long hours and days, and a lot of square footage. So we're involved with a lot of the ACI committees. You can't open up one of the documents in ACI without finding our names out there. ACI 360, Design of Slabs on Ground, is one. That is the document is a guide. There is the ACI 302 committee, Construction of Slabs on Ground. We're either president or past presidents or chairmen of these committees. 117 on tolerances. We run into a lot of tolerance conflicts in concrete construction. So there's a document that we've served on in the past. And then also a guide for design and construction of concrete site paving for industrial and trucking facilities. When you do a 1 million square foot industrial building with maybe 5 million square feet of suspended slabs in there, there's lots of trucks entering and exiting the property. And we felt that there needed to be a much cleaner document relative to industrial parking lots and truck courts. So we'll talk a little bit about that today. So first thing we're going to talk about is a little bit is the anatomy of an industrial floor slab. We've got our base materials that are local to the project site, and then our subgrade. In Ohio, you guys have a 304 material. You're blessed. If I could get crusher run 304 crushed stone in everywhere in this country, I would not have near the problems I have, but you would be amazed the variability in this base materials that are available throughout the United States. 304 is one of the best base materials I've ever worked with. We have a vapor retarder that is generally on top of the base material. And if you've got an air-conditioned building, just putting a vapor retarder there can save you 5 to 7% of your annual climate control expense. So we see this in most air-conditioned industrial buildings. 10, 15, 20 years ago, not too many vapor retarders used. Today, the vast majority of projects I'm involved with have a vapor retarder immediately underneath the concrete slab. Okay, Bob, still hearing everything okay from your end?
Everything's great, Rick.
Everything's great. Just want to make sure. All right. We have our concrete slab that sits directly on top of the vapor retarder. There's actually an ACI flow chart. ACI 302-2R has a current flow chart in it that talks about where the vapor retarder goes in various instances or different types of construction. With our floor slabs, we have what we call isolation joints. We rarely have an expansion joint in the floor slab, but a lot of people refer to expansion joints in industrial buildings. Isolation joints separate the floor slab from our structural elements like our columns. They also separate the floor slab from our wall system. So we have those in the building. We have construction joints, which are basically our day joints. This is the limits of our pour for a given placement. And we commonly do pours between 20 and 50,000 square feet. The largest that I've been involved with was 256,000 square feet in one day. And that was a large project down in Dallas that we did for General Motors. Then a lot of times we'll see keyways on industrial floors. We wrote keyways out of our industrial design documents probably 20 years ago, but we're still running into a lot of engineers that put this detail on here. You know, given circumstances today, we had a lot of problems with keyways on floor slabs as far as cracking off of the top side of the female portion of the key. So this was written out of our design documents years and years ago. So if you still have keyways on your structural drawings and details, we need to get those scrubbed off. Then we also have something called a contraction joint. We used to call them control joints, but that implies that we know what we're doing on concrete construction, and that may be a stretch sometimes. So we changed that terminology to contraction joint, because when we say control in a court of law, then the attorneys jump all over that, and contraction was just a much better way of saying we're trying to accommodate some of the shrinkage. If God's smiling on us and we do everything right construction wise, then we get this in joint crack. So basically it's a straight crack that we can resaw this joint with a special saw to clean the vertical faces and fill it with a semi-rigid filler, which is the cheapest way to fix a crack in the floor slab, if you will. If we don't do it right, then we get some of these things called out of joint random cracks, and that's typically what our clients complain about. And random cracks are misunderstood in our industry. If you do them right, in other words, if you over reinforce the floor slab and produce numerous tightly spaced cracks, that's not a bad design. It's just it's cracked, and so a lot of our clients, especially retail clients, just don't like to see cracks. So we'll talk a little bit about that when that may come into play. Let's drop all this stuff out of here and let's talk a little bit about the components of the floor slab as far as a structural perspective. All industrial floor slabs subjected to traffic should have some type of load transfer mechanism in there. First, we have a load transfer mechanism at our formed construction joint. And then secondly, we generally have a load transfer mechanism at our sawn contraction joints. Now that can be a dowel basket or it can be light reinforcing steel. And one of the reasons why I wanted to show this Did you hear the clicking noises? The clicking noises are those lift trucks going over the joints. And in the first video that was running, the floor had no load transfer in it. So all the joints were faulting and the lift trucks were riding over the joints. The slab was compressing on one side of the joint and it was hitting the bump. The operator was seeing a very poor ride. On the second one, we actually had a pallet rider that was running over the floor slab, and that pallet rider was destroying those joints within 7 months. So it's very important that we have positive load transfer in those floors. In the photos I'm showing now, we need positive load transfer in there for anti-fault mechanisms. This is actually a retail store. It's an integral color floor slab for a Walmart. And you can see that we've got about a 3/8 to a 1/2 inch fault in the floor. And that's as a result of a dominant joint that occurred in the floor slab due to a vapor retarder. So that's a trip hazard. And if you want to get sued as a retailer, all you need to do is put a trip hazard in a grocery store and shoppers will find it. And industrial floors, we don't want any type of faulting because we don't want chipping and spalling of the joints. So in this second photograph, I'm actually measuring the stability of that joint with a dipstick or a digital level. And I'm driving a fully loaded lift truck across that with a heavy pallet on the front of it to actually measure how much differential movement we're seeing. And we've got different levels of differential movement we permit in the floor slabs. And then based on that differential movement, we can come up with repair strategies that are appropriate for those conditions. So when we look at floors, obviously an unreinforced floor with no load transfer is the least expensive project to build, but it's the most expensive to maintain. So it's very attractive for speculative warehouse construction, for developers that are out there trying to hit a lease point as far as leasing the building, a cost per square foot. But you can see the kind of problems that we run into. We get a sophisticated material handling client in one of these buildings. The joints end up getting beat up. We end up with corner repairs in the form of structural nosing repairs. We end up with wide joints in the floor slab that start to widen out. Then we have repair contractors that use the wrong type of joint fillers to fix those. And if they do use the right type of product, like a structural nosing repair, honor the joint with a semi-rigid filler, which is the photo on the left, then you end up with a very expensive repair. These repairs will run $30 to $60 a lineal foot. On the right, we're actually showing that type of repair, a structural nosing repair that was done to the joints that were spalling. And if you notice the arrows that are pointing to the pins, those are actually ports. that were used to permit the undergrouting to occur. So this particular floor slab, they had 3/8-inch pilot holes that were drilled through the floor, alternating, and they pumped in a two-part modified foam to basically expand and reconnect the bottom of the floor slab with the top of the base materials. Okay. So if you do the floor slab improperly, as far as the design work, you can add $1 to $2.50 a square foot to repair those floor slabs. So many times those floor slabs, we talk to clients and they say, well, dowel baskets are too expensive or nominal reinforcing is too expensive. And we'll say, well, how much? And they'll say, oh, it adds 50 to 75 cents a square foot. And then we say, well, we're looking at $1 to $2.50 a square foot to repair the floor slab downstream if we don't do that. So be very careful when you're looking at these first costs that you are looking at, and comparing your options can be very, very expensive to repair in the future. If we use dowel baskets in the floor, I always stake them. I never allow the contractor to plop these things, and you'll see here the ready mix concrete hitting the top of the base. Any dowel basket that's in that path is going to basically float like a surfboard or get moved like a large wave hitting somebody that's standing in 4 feet of water. So we always want to stake those baskets. So you can see on the photo in the right that they have spray paint and string lines that are down to align the baskets, and the baskets are staked. The other thing we do is we never cut these tie wires. And there's been a little controversy about that in our industry. Are those wires too much restraint? I can tell you they're not on an industrial slab that's got joints that are 15 feet on center or less. We've never had a problem with those restraining activation of the saw cuts. Leave them in. That keeps the basket properly aligned, and it also prevents those plates or round dowels from falling out. So here on the left, I got called to a project in Tracy, California, where 45% of the joints in the speed bay were unstable, and the floor had baskets in it. When we ran ground penetrating radar across the floor, we found 45% of the joints where the basket was not in its right location. So you can see the saw cut up here at the top where the arrows are pointing, and there's the basket that's about 3 feet away. So we spent a lot of money on putting the baskets in the floor. They didn't stake the baskets. They just poured right over it, and the baskets slid. And when the baskets slide and they misalign, then you've got a risk of getting the crack outside of where the dowel is. And now you've got a crack in the floor slab with no load transfer stability. So that's always a risk. Another way we can put in load transfer in a floor slab is to nominally reinforcement. And ACI 360 gives us a couple of options for that. Anytime we nominally reinforce the floor slab, notice I'm toggling here, showing that the construction joint is widening if I put that in there. Reinforcing does nothing until the concrete cracks. Once the concrete cracks at these saw cuts, it's going to hold the saw cuts tighter than a floor that does not have reinforcing in it. And as a result of that, it sends a disproportional amount of shrinkage to the formed construction joint. That's called a dominant joint. So this joint at the saw cut may open up. Initial opening will be 1/8 of an inch due to the saw cut, and maybe an additional 1/16 to 1/8 of an inch of movement. And then this construction joint can actually open up 1/2 to 3/4 of an inch in width. I'll show you that in a minute. With fiber reinforcement, it's a very similar function. Whether this is high volume polymeric fibers or steel fiber reinforcing in 40, 50, 60 pound per yard dosages, once you put that amount of fiber in the slab, you're basically putting little tie rods across these in-joint cracks, and you're forcing that movement to another location in the floor. Here again, the formed construction joint. So we've done a great job in eliminating restraint in the floor slab, but it's come at a cost, and that's these joints that have opened up. Just want to illustrate to you some of the problems that we've had in the past with buildings where we've had dominant joints. So this is a large warehouse out in Pittston, Pennsylvania. And one thing I will tell you about Pittston is they have limestone that you can import from the Philadelphia area that has low shrinkage characteristics, but they also have sandstone in this market that's the predominant material. The sandstone has about twice the shrinkage that the good limestone has. So unfortunately, we ended up with a spec mix with sandstone, high water demand, and high shrinkage characteristics. So the building itself was laid out into 7 placements, or let's see, no, 10 placements, excuse me, 10 placements. So these red lines here are construction joints. We poured these left to right across the building. At all these red lines, we had dowels, 3/4 inch round dowels, and they used a system in here called a laser form, which is a partial depth form. Not a big fan of these types of partial depth systems myself, but the contractor used it and it was okay. Then the contractor went in, and this was a nominally reinforced floor. The contractor went into this project.
Yep, this one. Yeah, that link worked.
Okay, are you all still there? Okay, just want to make sure everybody's there.
Yes, I am. So I guess will a new link be sent out after for like the next ones?
Hey, Bob, we've got someone talking online. You might want to mute them. Okay, so on this particular floor slab, ACI 302 and 360 have a statement in the document that says, if you have a nominally reinforced floor slab, we recommend you break the reinforcing steel and slide in a dowel basket, which is the photo of these fellows up here in the top right. So basically they've got a reinforced floor. They broke the reinforcing steel every 125 feet and they threw in a dowel basket. That's these blue lines that are in these pores. I'll show you what happened. So we finished this project up in I think it was in the spring of 2010. By April, I had gotten called back to the project site. We had some random cracks in the floor where we had doubled up the welded wire reinforcing. That was an unforeseen problem there. But then we started seeing these areas with the blue where we started getting what's called dominant joints in the floor slab. And every 3 months or so, I got called back to the site again, and I had to continue repeating my visits to this site until basically every dominant joint in the floor, every 125 feet, had opened up. Now, we went in and filled these joints in the summertime, sometime around August. And after we filled those, I got called back in to troubleshoot the joint filler that was actually extruding out of the floor. So what we found is that the sawn contraction joints opened very little. Then any type of thermal warm-up that the floor slab experienced all channelized to one location every 125 feet. That caused the semi-rigid joint filler that we put in the floor to bulge out of the floor, where the lift truck was more than happy to come in there and shear it off. So be very careful about discontinuing your reinforcing in a nominally reinforced floor slab. You can run into some significant challenges with that. Okay. Also at the construction joints, which are these purple lines running here, we ended up with joint filler that sagged and dropped, and we ended up with some wide joints that curled. We had to come in and grind those down. You can see the lippage that was occurring here. And then we started to see joint spalling. And all of this occurred literally within 1 year of this project going live. You can see here the joints are actually 1/2 inch in width. So we had two forces at play. We had drying shrinkage in the floor slab, which takes years to release in an industrial floor. So for an 8-inch thick floor slab, we might be looking at 40 to 42% of the drying shrinkage in the first year, and then perhaps 60% after 2 years. It starts to tail off after that, but in these first years or so, in the first literally 6 months, we see a lot of that shrinkage that occurs, and then it just kind of slows down. So give yourself some time and do not expect that you're going to fill these joints one time. This is a multiple step process. The second component we were facing on this was thermal. And the one thing that we cannot fix with any shrinkage reducing admixtures or with any of this technology that is out there for limited joint floors, we can't change the thermal properties of the concrete. It's going to expand and it's going to contract based on the type of aggregates that you have in that concrete and where you're located in the industry. So I've got probably more floors instrumented in this country than anybody as far as slab surface temperature, humidity, dew point, and ambient temperature. And I monitor these buildings from time to time, go in and look at where the readings are. And you can see here in Jacksonville, Florida, that the temperatures are ranging between 67 to 85. And then if you look at Florence, I mean, it's someplace between 60 and 74. It's a 14-degree delta between those two, almost a 20-degree delta from Jacksonville. So that thermal expansion will release between your joints. And if your joints are 100 feet apart, it could cause an 1/8 of an inch movement. If your joints are 14 feet apart, maybe 12 thousandths of an inch movement. So thermal becomes a big player when you're doing limited joint floors. ACI doesn't cover a lot of this on our committee documents because we assume you're saw cutting those slabs 15 feet on center or less. And here's the old rule of thumb, the 2 to 3 times the depth of the slab, and then joint your slab accordingly. And when I was in the steel fiber business, we commonly jointed slabs 25 and 30 feet apart. And did I get into trouble? So when this chart was produced, this chart includes curling stresses and some other things in it. This keeps us out of trouble. And without question, if you ever want to know how far to joint your floor slabs, 15 feet on center or less is going to keep you out of trouble 90% of the time. Okay. So we have a lot of people coming at us saying, hey, we want to get rid of the joints. We understand that this is the hot thing to do in our industry. How do we do that? So, here's a floor slab right here with 50-foot columns, 12.5-foot joint spacings. And then you start to look at your shrinkage over the 15-foot versus your thermal over the 15-foot. And then here again, you've got your 50-foot column spacing and looking at your shrinkage, which might be about 0.4 inches, and your thermal, which might be 0.04 inches. And then you look at maybe going 150 foot by 150 foot. Now you're looking at over 1 inch of shrinkage and 1/8 of an inch of thermal contraction and expansion. Now, the shrinkage eventually is going to slow down and stabilize, but that thermal expansion and contraction, it will never stop unless that building is climatized. And when I say that, I mean it's got to be held within about a 3 to a 5 degree delta. So be very careful when you start looking at this, because with a tightly jointed floor, we may have to fill a little separation that occurs, and then that's eventually going to go away after 2 years. But with these wider joint floors, 50-foot and 100-foot spacing, you're going to have movement that is going to continue to occur and release at those joints. So you want to put those in areas of the building where they're not going to see traffic, or you need to be prepared for that if it occurs. Okay. So we were talking about reinforcing. Let's talk a little bit about how much reinforcing. Well, the buildings are getting taller, but we generally don't size reinforcing for the thickness of the floor slab. In other words, if the loads are increasing, I don't change the amount of reinforcing that I'm putting in there for a 6-inch slab. All right. So as we see the buildings hitting 36 and 40 feet clear, the number of pallets you can put in those racks increases. And we're commonly seeing, and I've been running these stress calculations now over 30 years, 7 and 8 pallets put in these racks. And we've got forklifts that'll lift them up that high. A lot of our clients design their floors for 2,000-pound pallets. And at 2,000 pounds, you're just not going to see 6 and 7-inch floors out there that'll carry those loads anymore. So the new standard that we're typically seeing is an 8-inch slab with about number 3s at 16 inches on center in it, or an equivalent 8-inch slab with dowel baskets or something similar to that. We wrote an article that's on our website, and if you went to our domain, which is ssiteam.com, you can find this article and download it. But ACI gives us guidance on what to do if we're using light reinforcing, this 0.1% steel that you see, or number 3s at 16, number 3s at 18. It tells us to joint the floor slab 15 feet on center and put that reinforcing steel in the floor and locate it at a position where you're not going to saw cut through it. ACI also gives us guidance on how to produce limited joint floors that have no saw cuts, purposely installed saw cuts, but are designed for serviceability. So basically a floor slab where we want millions and millions of tiny, tight little cracks in it. And there it tells us to go to the 0.5% cross-sectional area steel. What ACI doesn't tell us is what to do in between. There is no guidance in our committee documents that says what to do if you're using between 0.1% and 0.5% steel. So we call this the courthouse zone. And we commonly run into floor slabs that are designed with code minimum reinforcing, 0.18%, and these are right smack dab in the middle of the courthouse. Here's an example of what happens in a courthouse floor. Number 4 bar, 18 inches on center in a 6 or a 7-inch thick slab. The saw and contraction joints never activated. You can see that the reinforcing steel was jacked up in the floor slab just a little bit, and they got some settlement cracking over the bar. You can see where every rebar is in that floor slab. Now, the good news is we'll never have to refill these joints. The bad news is sawing out and filling these cracks will run anywhere from $9 to $15 a lineal foot. So it gets very, very expensive. And this entire floor slab, 1 million square foot, had 16 miles of out of joint random cracks in it. So you can do the math yourself. So limit the amount of reinforcing steel to less than 0.1% if your intent is for that saw cut to activate. And if your intent is to get rid of the saw cuts, jack it up to that 0.5% reinforcing steel and do away with them. But stay out of the courthouse zone. Okay. Anytime you reinforce the floor, you force that disproportional amount of movement to the construction joints. This is a tilt-up building in Dallas, Texas, with a vapor retarder poured under a portion of the building. I've got lateral load path steel connected to the tilt-up panels in this first bay. So all the movement that was occurring in that first 100-foot wide pour released at this construction joint right along column line 3. And it opened up 13/16 of an inch in width. I do not have a joint filler on the market I can stick down in that floor that is going to take that expansion and contraction and then that additional shrinkage that's going to occur over a time frame. So I'm forced to go in there and rebuild those joints with a structural nosing repair material at a cost of $30 to $60 a lineal foot. So that's what we ended up doing on portions of this floor after we tried numerous times to fill the joints with different products. And then we saw that joint filler actually extrude up out of the floor. For that reason, we developed what we call the hybrid joint. Anytime I do a reinforced floor, I lightly restrain the construction joints with a little bit of reinforcing steel. So if I've got plate dowels in the floor slab, 24 inches on center, I alternate those plate dowels with a number 3 rebar to basically force the shrinkage back into the saw and contraction joints, and a little bit of that shrinkage can accommodate itself at the form construction joint. So we've been doing this for the past 6 years on every one of our big industrial projects, and it's working lovely. I've had 4 failures to date. We understand why the failures occurred. We allowed some of the engineers to space these out 36 inches apart. That was too far apart. We overstressed the bar and snapped it. And once you broke one rebar, it was like a zipper. It went down the entire construction joint and the joint overactivated. But this joint has been working very well for us. It's used on all the Home Depot, Amazon's large distribution boxes that we have out there today. As I said, you can over reinforce the floor with 0.5% steel. We do that when we're pouring F-min floors or super flat floor slabs. We don't want any saw cuts in those because we don't want any curling at the joints, and we want that floor to have perfect rideability longitudinally and transverse, or left to right over the wheel path. Also, we get involved in floors that are heavily reinforced if we've got steel wheels or very, very hard wheels on the floor and we can't get in there and maintenance the floor. So here's an F-min floor on the left where we can see the forklift is extended, and what we're trying to do is prevent that forklift from running into the racks. So we have that floor poured very flat and very level. And then that same floor over here, you can see the grinding marks that were done in the aisle to bring that floor in compliance. For those of you in pavement design, you might call that IRI, your international roughness measurement. We use the same type of equipment that you guys use to measure those floors. It's called a profilograph. Okay. As we get into these taller buildings, one area that we're getting into trouble with are overturning moments. And as these buildings get taller and taller and taller, we're seeing very high uplift forces in these floors, especially in high seismic areas. So something I just want to point out to you. A lot of our clients come to us and they say, hey, we want these racks to be designed for 2,000-pound pallet loads throughout, or 2,500-pound pallet loads. And so we'll ask the question, how many of these pallets do you receive on a given day that are going to be that heavy? And well, that's a good question. So they'll go back and they'll do the math. So here's a building where over 5,000 pallets that are received are between 1 and 600 pounds. And then only 23 pallets out of all the pallets that came in there were between 2,600 and 3,000 pounds, and only 62 in the entire building were over 3,000. So we're like, why would you design the floor slab for a 2,500 or a 3,000 pound pallet load if the majority of your inventory was in the 1,000 pound pallet load or less? So be very careful about that, because these particular floors with these high uplift stresses can require 8, 9, and 10-inch thick slabs when we only need 7 or 8-inch slabs to carry it. So if we know that we're going to have these heavy pallets, ground stack them. So instead of putting them in the racks, we put some labels on the racks to basically say any pallet that's over 2,500 pounds goes on the floor, not into the racks. Okay, limited joint applications. This is Mirage tile on the left. If you buy tile from Lowe's or Home Depot, and it's a large 16-inch sheet goods, these are automated storage retrieval vehicles that'll go into the kiln and pull out these drying units. And they want no joints in those floor slabs as a result of the robotics. And then this little floor over here, this is the Dallas Cowboys merchandising stadium facility. It's where they sell all their merchandise. We don't have a good football team, but we do sell a lot of merchandise. This is an integral color floor slab. The joints in there are fake joints. We cut those in with what's called a mongoose saw. That floor is a pile supported slab, and it's heavily reinforced for crack width serviceability. So I wanted those cracks to be less than 15 mils on center. This is the kind of reinforcing I'm talking about. Another thing that we're running into are ground improvement sites. Floors that are built on controlled modulus columns, stone columns, wood piles. These types of floor slabs need bottom reinforcing so we can span between pile to pile or rigid inclusion to rigid inclusion. We load this type of a floor slab up with this particular floor has number 7s at 10 inches on center. It's got 65 pounds per cubic yard of steel fiber reinforcing. And then we use a special joint along our free movement joints that is basically shaped like a sine wave. That joint's allowed to open, and there's actually a stay in place keyway, metal keyway, that is designed for load transfer that I can rest my semi-rigid joint filler on. So we're seeing a lot more of this type of design coming out, especially where we're getting into these ground improvement sites. And then, of course, wouldn't be complete if we didn't talk about one of the largest e-commerce companies in the world. This is a Amazon industrial floor slab. We do all of the Amazon projects. The slabs on ground are poured normal with joints in the floor slabs, but the suspended slabs are heavily reinforced. Beams on an 8 to a 10 foot spacing with an 18 gauge, 1.5 inch deck, 6 inches of concrete, 4.4 D11 to 4.4 D14, I think is about the biggest that we've gone on these. And then 7.5 pounds of macro synthetic fibers per yard of concrete to help control the cracking on these decks. One of the things we have to be aware of on these decks is that we have very heavy equipment that's up here running around. So as we're placing these floor slabs, the engineer record needs to be aware that I've got 2,000-pound pieces of equipment up here. They're basically small market platform type laser screeds that are striking off the concrete to a level elevation. And actually, when we pour these, this is our expansion joint here. We actually pour right across the expansion joint with a fake wood form in it temporarily, come back in and cut that form out. And then we come back and we put in a Watson Bowman armored joint there. Anytime I do a limited joint floor, I like armored joints. So armored joints are traditionally used in shrinkage compensating floors. You typically have very small wheels running on these floor slabs, which is influencing the owners to get rid of the joints, because these small wheels are very problematic for jointed floor slabs if the joints are not properly maintained. The armored joints, stay in place joints at our construction joints, and now full depth armored joints at what we would call a purposely induced joint at a normal saw cut location. And here's the enemy. We did not get the memo on this years ago. We used to see a lot of counterbalance lift trucks in buildings, 2,500, 3,000 pound capacity lift trucks. And today what we see are 4,000 and 5,000 pound stock pickers that are out there. We see these pallet riders, which are on the bottom left. That's the most abusive piece of equipment in the building. Some of these are 3 deep pallet riders with 6,000 pound point loads coming down on these wheels. The contact pressure we have calculated from these wheels is 1,600 pounds per square inch. It will eat a joint up. So if the joint is not properly filled and maintained, it's a major problem. On limited joint floors, as I said earlier, the biggest drawback is that all that thermal expansion and contraction continues to release at one part of the floor. So you have to go back in and maintain these floors on a regular basis. So the picture on the left is what I saw about 6 months after the building was completed. And then I went back to the building in March of 2017, over a year later, and they had just touched up the joints. Notice the width of that joint is approaching 3/4 of an inch. It was a 1/2 inch at year 1, 3/4 of an inch at year 2. So you're moving a lot of movement there, and you have to deal with that thermal expansion and contraction. Here's how not to do joints. These are also limited joint floors. The contractor, for some reason, put in a 1/2 inch tooled edge on a construction joint, which is a big no-no on any type of an industrial floor. If we put an edger in the floor slab to identify the construction joint, we always drop a saw in there and square that joint up before we fill it. They did not do that. You notice that the joint filler has been smashed down into the joint, so it's not protecting the edges, and the edges are now starting to round over due to traffic. So they've gone in, and here's the original joint filler that's shown on the in the right photo on the right. It's in there about a 1/2 inch in width. Here's the touch-up filler, and now here's the new distress. They need to square the joint up and put new filler in there full depth. And here again, that joint's over 1.5 inches in width now as a result of improper maintenance. On all industrial floors, we always fill the joints. We put in a semi-rigid epoxy or a semi-rigid polyurea in the floor slab. We may have other factors like flatness and levelness that are specified. Gloss, distinctness of image is another property we can look at. Slip resistance and roughness. So for the Amazon program, we actually designed their floors for gloss and roughness right now to make sure that the robotic units do not spin out on the concrete. Here's some of the devices that we use to measure the floors: a profilograph at the left, a gloss meter, and then here's this BOT 3000E, which will test for slip resistance. Anytime you do polished concrete, where you're going to have a lot of people coming in and out of a building, not a bad idea to run this test just to make sure you've got a piece of paper that says your floor is not too slippery. The other things we look at are the curing compounds, sealers, densifiers, and dry shakes that may be on the floor. So I'm not going to spend much time on concrete mix design, but I just wanted to give you a couple of real quick little notes here. One is, make sure you've got enough cement in there to coat the aggregates and the fibers. We can easily make 3,500 and 4,000 PSI concrete, but in the winter time, we need more cement to get set. And so a lot of times I'll see spec mixes come across my desk that are suitable for summer construction, but not for winter construction. Get the cement in there. That's your biggest advocate. Make sure you're using the largest well-blended combination of materials possible. If you've only got a 2 aggregate plant, you can't run 1.5 inch stone in there with a natural sand or a blended sand. You're going to end up with problems as far as finishability. So I would drop down to a 1 inch well-graded stone and then go with natural sand. ACI does like sand, natural sand in the concrete. And if you do use manufactured, put 30% natural in there to round off those particles. And then water is not the enemy. I like water. I like a 2 to 3 inch water slump. Water cement ratios of 0.47 to 0.55 are extremely common on industrial floor slabs. Anything less than 0.47, you're starving the concrete as far as water. You're dealing with a chemical slump, and those chemicals will create problems for the floor finishers. And then, unlike pavements, no air on industrial floors, less than 3% in trapped air. So, good rule of thumb that was told to me years ago for industrial floor slabs. First, I like a 5 plus or minus 1 inch slump at the placement, point of placement. And that's defined by NRMCA as the slump of the concrete coming down the chute of the concrete truck, hitting the ground, or coming down the chute of the concrete truck going into the pump. So that's always where I do my acceptance for slump, air, temperature, those kinds of things. If the contractor wants to slump at the end of the line, I'll be happy to go out there and slump it for him. But compliance and as far as acceptance or rejection, it's occurring at the hopper of the pump, or it's occurring as it comes off the truck onto the ground. Very few contractors pour a 4 inch slump. So I'm not quite sure why ACI says maximum 5 inch slump. That's going to come out of the 302 document if it kills me. Another thing we look at is trying to use the biggest stone we can. But in general, 520 to 540 pounds of cement or cementitious is a great starting point for our industrial floor slabs. The reason why we like good, well-graded aggregates is for what you're seeing right here. These were 4 cores that were taken out of a floor slab that were poured at 2 different times. The first slab, core number 4, was placed, and that was 1 million square foot of plant. They added on a 500,000 square foot addition, which are cores 1, 2, and 3. Believe it or not, the concrete, the mix design, the aggregates, everything was identical from the original plant to the expansion. But look at the change in the aggregate grading and the aggregate fracturing that was done by the quarry. We ended up on this particular project with something called aggregate shadowing. And so they went and pulled the same mix design, same aggregate source, same concrete supplier, and we had aggregate shadowing all over the surface of the slab, which led us to mortar flaking. And once that started coming off the floor slab, it was a nightmare from a serviceability perspective. So we commonly recommend what's called a roller bug. We laser screed the concrete. As soon as we laser screed the concrete, we run this roller bug out there to push down those large aggregates, and then we hit it with a channel float or a check rod and smooth it out. And you can see you get a nice cream up on the surface here. So when we place our double trowels on there to finish the concrete, no more aggregate shadowing. And this by far has saved our keister on a number of large projects. This project on the left here that I'm showing with the curing blankets was actually done up by Troy, Ohio. It was a large Home Depot project. I'm going to talk about curling real quick. Differential shrinkage. Basically, that's what curling is. So the concrete shrinks differently on the top than it does on the bottom. And as a result of that, as it's drying, the slab loses water and it lifts off the base. And so this is not that far off as far as scale. We typically see curling occurring 2 to 3 feet back from all the joints. And if you were to core the concrete and take moisture of the base and the concrete moisture at the bottom, it would be darn close to 100%. So whatever the differential RH is top to bottom, that gives you that curl. I've measured this with internal relative humidity probes, and you know, if you look at underneath the slab, you're at 100% RH, but just at 5 inches down, you're at 90%, and 1 inch below, you might be at 80 or 85%. Well, this is why your moisture sensitive floor finishes fail, and this is why sometimes it takes a while for us to dry out these buildings. Curling changes in the country depending on where you are. So down in Houston, where we have high relative humidity, even the construction joints don't curl very much. In fact, no saw cuts have curled on this building after 2 years of service. But go up to Eagan, Minnesota, look at the curling that occurs there. And those of us that live down in Texas, where it's warm and moist, our skin doesn't dry out like it does when I grew up in Ohio. In the wintertime, when your skin starts to dry out and you get out of the shower and your skin starts cracking and it hurts, that's what that concrete slab's feeling. And so Eagan, Minnesota, we had extremely high curling up there as a result of the very, very low relative humidity. You look at these floors, they're not jointed that far apart. I mean, 15 foot on center joints. This one over here is looking at 0.8 of an inch curling at every saw and contraction joint. Okay. So this is what curling may look like. You go across the floor slab, you get to the far end. And this is why I had got in trouble when I was doing steel fiber work, is I used to joint the floors far apart, and the panels got so far in width that the curling stresses were high, and I got mid-panel cracks. And I didn't know that until I met Jerry Holland. I actually hired Jerry when he was with Lockwood Green to help me evaluate a floor slab that had a bad curling problem and a cracking problem, and he educated me on this whole process. So here's a building I measured in Chicago 2 years after it was completed. The F numbers initially, when it was placed, were FF50, FL35 and higher. After 2 years of service, curling has developed at all the joints, and the F numbers have decreased. The flatness is now 24 and the levelness is 19. So notice here on the column spacing, we got 50-foot columns between M and N and 60-foot columns between N and P. So the contractor jointed this floor 12.5 feet on the 50-foot grid and 15 feet on the 60-foot grid. Look at the curling difference, 0.2 of an inch of curl over 15 feet. But as soon as I got to the 15-foot joints, 0.4 of an inch curl, almost doubled the curling that the equipment was feeling. So that creates problems for us. Now, a lot of our committee documents currently say that vapor retarders increase the amount of curl. And I'm here to tell you that those statements are wrong, and those statements are unproven. I've actually gone out and measured hundreds of floor slabs with and without vapor retarders, sometimes in the same building, like this one here. I've got a small trucker's lounge here where I've got 2 bays with a vapor retarder in it. I took a curling profile run 5 across the vapor retarder at the same location on the same pour. I took run 6. So we're going to compare those 2 elevation profiles. Run 5 over the vapor retarder, the F numbers are 8447. Without the vapor retarder, 5642. So the floor is actually flatter and leveler with the vapor retarder. Now, if we go back and look at this again, look at run 7. It goes over the vapor retarder to the first bay, then the vapor retarder stops, and the next 50 feet have no vapor retarder. Let's look at what happened there. Here's no vapor retarder from the pour back strip to the first column line at 60 foot. You can hardly see the blip on the radar as far as the elevation change, but look what happens between 60 and 105 feet. Now we get that 0.2 of an inch curl and a very defined curling profile. The reason why this occurs is the base is at 100% relative humidity. Now, everything I'm talking to you about is everything that I believe in, and many others do as well, but I practice what I preach. This is actually my workshop that I'm getting ready to pour at my house. It's got a vapor retarder in there, a good 10 mil ASTM E1745 vapor retarder. It's got chairs in here holding the reinforcing steel in the right location. Number 3's at 18 inches on center, and that's very common for us. Anytime you have moisture sensitive adhesives, you want a vapor retarder. Anytime you're trying to avoid sweating slabs, you want to make sure there's a vapor retarder in there. And you can see this area on the left had the vapor retarder, no vapor retarder on the right. Vapor retarder on the left, where we're just dealing with calcium and potassium hydroxides that are coming up through the concrete as it's drying. No vapor retarder on the right. Now I'm adding in hygroscopic salts that are coming from the soils underneath. And if you want to attract moisture, just put salt on top of the floor slab. Same reason why you put salt on a bridge deck, trying to get it to attract that moisture and melt the snow and the ice. So we have more problems where we don't have vapor retarders than projects where we do. These are the areas that I'm troubleshooting sweating slabs right now. Here's the new ACI 302 flow chart. And by the way, for Ohio Concrete, I will be providing you guys with a PDF of the presentation at the end. So if anybody requests that, just let me know if you need that. If we put in the vapor retarder, we always make sure we put it in the right spot. In this case, they put the vapor retarder over the welded wire reinforcing, and everybody just stood there and looked around and it ignored it. But want to make sure the vapor retarder is actually below the reinforcing steel. That would be a good start. Other ways to mitigate sweating slabs: large destratification fans to help push the air, the warm air, down to the floor slab to warm the floor slab up so that it's higher than the dew point. The last thing I ever want to do is shot blast the floor and open up the pour voids. That's just going to be abrasion resistance nightmare for us. So be very careful about that. People will say, well, let's do the concrete fuzzy. Anytime you lightly finish the concrete, you're going to see more abrasion resistance, especially if you get the wrong type of lift trucks in the building. I prefer to resolve the problem with some type of an avoidance system that's interlinked with our exhaust fans, and basically burp the building or blow out the building when I have periods of low humidity. Okay, what else? We need to deal with the weather when we're placing floors. ACI's got some nomographs that tell us when we need to protect slabs as far as rate of evaporation. I'm here to tell you that we've been measuring this for years using these Kestrel devices. Here's a Kestrel device that's set up on a small little photographic tripod. This device is interlinked with a cell phone and sends you a note when it's time to deploy evaporative retardants or fog the slab. ACI currently sets that limit at 0.2 pounds per square foot per hour is their recommendation. I want to tell you it's 0.1 pounds per square foot. Once you hit rates of evaporation higher than 0.1, you better start deploying Confilm, Eucobar, or some other type of monomolecular film out there to keep that slab from evaporating too quickly. I love fogging, but most contractors don't like to do it because they think it's too expensive. There are large fogging machines. There's one out there called Movavi that'll fog 40,000 square foot of industrial floor in one pop. Another thing to watch out is thermal contraction. We place a floor slab, it's in nice warm weather, and then all of a sudden somebody forgets to shut down the building over the weekend and we get a cold front. And then the cold front contracts the concrete and it pushes up against steel or something and it cracks. So thermal shock creates a lot of problems for us. And then finally, watch your carbon monoxide. We limit the carbon monoxide to less than 15 parts per million when we're pouring concrete. Make sure we don't carbonate that slab, which is a permanent defect. Be aware that the heavier the equipment we put on the floors, the better we compression dewater that cap. And a nice report that was done by Skirdo, or sponsored by them in Chicago, shows that when they were finishing concrete with a 1,000-pound rider, they got a very, very thin compression dewatered cap. But when they power trowed it with a 3,000-pound rider, the compression dewatered cap was several millimeters in thickness. Thank you, Amy. So as you're looking at this, this will affect your moisture sensitive floor finishes. If you're trying to fast track those and get those on a building, you want that concrete to dry out quicker. So if you really compression dewater or burnish that floor tight, you're going to need to grind that floor to get that off the top. This was a Nebraska Furniture Mart where they had applied a cure and seal product to the floor and hard troweled the concrete. Architect made a mistake. When I measured the relative humidity, we were at 93% RH, and that was after months of drying. So we had to take the cap off the floor. We always fill our joints with a semi-rigid joint filler. Be aware that some of these epoxies can UV discolor. So you want to make sure you do a test application first, and we never allow backer rods underneath the semi-rigid joint fillers. More and more of our customers are pushing us towards polyurea joint fillers. Just be aware that these polyureas set very quickly, and the dwell time is so short that sometimes the joint filler does not get to the top of the saw cut shelf that we put in there. We call that the Glidden paint can effect. So as a result of that, we need to make sure that we slow those products down a little bit. I always do a proof roll on my slabs. If we have rutting of this nature here, we haven't done an adequate job on prepping our base. This is a project in Texas where they said, oh yeah, the pad's good and tight. And we drove the concrete trucks in there, and that was it. We weren't pouring the concrete. So here again, I would love to get your 304 crusher run down here in Dallas. Rutting like this will affect our slab thickness, which is problematic. This is actually supposed to be a 6-inch thick slab. We cored it 10 times, and those were the random cores we pulled out of the floor. We obviously have a rutting challenge on our hands. Anytime that comes up, I always use an impact echo device to measure the floor slab thickness. Much, much cheaper than doing cores, and very, very effective. Let's skip through this real quick. I want to get to this last little section on industrial pavements. So I told you we do a lot of industrial slabs and we do a lot of industrial mezzanines. So here's our industrial pavements outside. A couple of things that we've noticed. One is, you see how that's a 53-foot long container? When I was growing up in Ohio, we were at 42 foot. So what happened? Well, we put 53 footers out there, which means that we put a disproportional amount of weight on these front outriggers. Now, this is never checked in our design criteria. So here are these outrigger loads out here that are 26,000 pounds each, separated by a walking distance between the trailers, which means I got a lot of load, 50,000 pounds coming down on this floor slab over 2 or 3 feet. And every one of these dolly pads were cracked across this building. So a couple of things to think about. One is, we do not include a dynamic load or an impact load for dropping these containers fully loaded on pavements. We're not using a over-the-road legal truck on a lot of these industrial sites. So check to make sure that you do not have these terminal tractors out here. Terminal tractors use hydraulics, and they may be a single axle that rapidly drops that container on the pavement. Add in an impact factor of 1.3 to kind of protect yourself from that. So instead of it being 34,000 pounds coming down on a dual axle, it's 34,000 pounds coming down on a single axle. That can add 2 inches of concrete to your design. So be aware that things are changing out there on our industrial pavements. And here again, nobody sent us a memo. Okay, I think I finished up in proper time. So Amy, I'll be happy to answer any questions you may have.
All right, Rick, this is Bob. I'll take over again. Can you hear me, Rick?
I got you loud and clear, sir.
Okay, there are 3 questions we have at the moment. Everybody feel free to put your questions in the Q&A box. I'm going to read them for the benefit of everyone, and we'll go through them one at a time. The first question is from John Bayer. We work on freezer buildings with thermal blocks that are 6 inches tall under columns at braced frames. We have been asked to transfer large forces directly into the floor slab, rather than down through the column base into the foundations. Have you seen this on projects, and are there advantages and disadvantages to this approach?
I'm seeing it every day of the week, John. So on the Amazon program, we build these 1 million square foot distribution centers, and we have isolated foundations for our column loads and for our mezzanine loads for the multi-level platforms. So typically they're on like a G4.5. There's 5 levels of mezzanine in these buildings. All of a sudden, we started seeing 30,000 to 50,000 pound point loads that are being supported by the floor slab as a result of a third-party mezzanine or platform for Intelligrated and some other companies. So typically what we're seeing are posts 16 feet apart, 15 to 16 feet apart, 14 by 14, 16 by 16, or 18 by 18 inch base plates and heavy loads. Now that creates a couple of problems for us. One is we need to circle back with our geotechnical consultant, because the geotechnical report probably referenced 500 pounds per square foot non-uniform live load as far as their assumption of the floor slab loading and what that was going to do to the long-term compressibility of the soil. So the loads you and I are talking about right now are going to exceed that 500 pounds per square foot by a fair margin. So we need to circle back with them and talk to them a little bit about that. Number two, we may end up, if the slab thickness cannot be increased, that's when I have to put that heavy bar down in the bottom of the slab. I get rid of all the joints, I load it up with steel fiber reinforcing, and I push all that shrinkage or movement out to the armored joints. The picture I showed you earlier of the number 7 bar, 10 inches on center, that was actually an Amazon job where a mezzanine hit us at 0 hour. I was not allowed to increase the slab thickness because of this ground improvement and stone column system I had. So I was forced to put that heavy reinforcing in there. So hopefully that answers your question, but we're actually writing a paper on that right now. And we're putting in the next ACI 360 document, a section in there on designing for building code loads. So when you have these mezzanines, sometimes you've got a lot of people up there, and sometimes they're maintenance mezzanines, and sometimes you got thousands of workers on them. So the building code may start to creep in there. So we actually put a little section in 360 on how to design for that.
All right, great. Thank you, Rick. Second question. This is from Ed Evers. What is your opinion on ductocrete, number 1? And then I'll let you answer that. Then we have a second question from him as well.
Okay. So I'll be able to answer that. As far as ductocrete, Primex, there's Mega Slab, there's shrinkage compensating floors. All these are what we call limited joint floors, and steel fiber slabs as well also would factor into that, and that'd be a high volume fiber slab. Anytime you do a high volume fiber slab or you do a limited joint floor with one of these technologies that are out there, you're always going to have those dominant joints that I'm talking to you about at 50 and 100-foot intervals. So the important thing is that, one, we communicate that expectation to our client, and that we let them know that the joint maintenance over the first couple of years can be pretty high, because we're going to have to wait for that thing to settle down to finally get the joint filler stabilized. And then we're always going to have some movement in the form of thermal expansion or contraction that's going to develop at that joint, and it's going to create some problems or challenges for us. So here again, whether it's ductocrete or it's any of these other systems, they're perfectly fine as long as we understand the risks of dealing with those joints every 50 or 100 feet. As far as outriggers on the floor slabs, I've got a section in my pre-slab agenda where I deal with this. The outrigger stresses can approach 80 to 100,000 pounds of force. And so floor slabs are just not designed to deal with that. So typically what we'll do is we'll put railroad tracks down or timbers down. We'll put a steel plate in between those. We'll sandwich another layer of railroad tracks. We'll put another steel plate on top of that, and I use that for my outrigger to transfer that load out and redistribute the force over a larger area. That's number 1. Number 2, anytime I've got pump trucks or a crane outrigger on the floor for hanging structural steel, or concrete trucks on the floor slab, I keep them 3 feet away from my free edges, which are my construction joints, and I straddle my joints. I drive that equipment right over the intersection of the saw cuts, never allowing those outriggers to touch down on a corner or on an edge of a slab, always in the center of the panel. But it's a risk. You got to be a little careful. I had a crane down in a project that I did for Daikin. it was a 220 ton crane on this particular floor slab. And literally I could walk right down the middle of the building and see where every outrigger was. It stopped. And then I thought, oh, well, they stopped hanging the steel from the crane this way. And they said, oh no, we just moved it over one bay. And so we walked over one bay and the cracking started right up again. So it's dangerous. I try to keep the crane tonnage to about 80,000 pounds in that ballpark. If I can keep it in that ballpark, I'm in pretty good shape.
All right. Hey, Rick, a follow-up question from John regarding the freezer building.
Yeah.
A little scroll down a little bit. I'm going to jump in here. He was actually asking about in-plane lateral load pushing out of the column directly into the slab.
Okay.
If you could address that a little more.
Yeah, so he's got a lateral load path type condition where he's having to take that thrust in there. If they have to do that, I'm going to have to over reinforce the floor slab and basically get rid of all the saw cuts and make the floor slab more of a structural slab. Anytime you put lateral bars back into the floor slab, like a moment frame type connection or something, or if you've got something of that nature, you either need to get that out of play and below the floor slab, or if it's in the plane, as you're saying here, then you basically have to get rid of the joints, and I would over reinforce the floor slab with 0.5% steel, and just make the whole floor slab a thrust block. So that's a great question, because anytime that you have a nominally reinforced floor with joints in it, and like on a freezer floor, as soon as that steel stops or you get to the first joint, you're going to accommodate 60 or 80% of that movement is going to snap right there. And that's going to be a major problem on a freezer floor.
Okay, great. Two more questions. One from Dane Redinger. And what device do you use for your floor profiling?
Okay, so if I'm doing random traffic floor slams, I use one of three devices, either a dipstick from the Face Company, a D meter from Allen Face, or I use a device from Somero Matson called an Axion, A-X-I-O-N, I believe is the spelling. That's a newer device that's available on the market. These are all toe to heel devices. They don't roll. If I'm measuring a defined traffic floor, I use a profilograph, and that's a special device, just like you would see on the highway, for measuring the difference between the left and the right wheel path and the front and the rear axle.
Okay, great. Two more questions. Another one popped up, but here's the second one in line. It's a great question. What type of curing do you recommend versus what actually gets put down? So that could take an hour, but give us a quick one.
No, that's a good one. So as far as the curing, first of all, ACI gives us no credit for the compression dewatering that I talked to you about earlier. So when Skirdo did this testing, and this document was called Self-Curing Warehouse Floor Slabs, when they did this testing, they had walk-behind power trowels on the floor that weighed 300 pounds, double trowels that weighed 1,000, and double trowels that weighed 2,000 or 3,000 pounds. And we saw 3 different compression dewatering, and we saw 3 different moisture retentions underneath those slabs. So ACI doesn't give us any credit for that. All the curing standards, 309 and 1315 that we use for industrial floors, were designed to be put on a wood floated specimen and tested in a oven for 72 hours. How is that even close to an industrial floor slab that's been compression dewatered with finishing blades? It's not. So as a result, we just had a major conversation about this in our ACI committee meetings on Monday. And more the industry is leaning towards floor slabs that are cured with a thinned down version of an ASTM C309 curing compound. My favorites are the resin-based cures, but even those products become expensive to strip off the floor. And when I say that, if I'm spending 10 cents a square foot on curing, I'm spending 30 cents to 50 cents a square foot to get it off the floor. So be careful. Now on exterior pavements, I go with the 1315 curing compounds. I let them sit there for 1 season. Then I go in and scrub the pavement, and I put down a silane or a siloxane type sealer or a lithium silicate that's got 244 behind it. That'll give you that good resistance to salts. On a lot of my floor slabs, we early age densify these floor slabs with lithium, potassium, sodium, or colloidal silicates, and then we put a sacrificial cure over the top of those, very thin to win, 400 to 600 square feet per gallon. Great question. All
right, and Carlo's got a follow-up. Do you see any finishing and or aesthetic issues with your use of microfibers?
With microfibers, no, not really.
I'm sorry, I apologize. Macrofibers.
Okay. No. So on the Amazon program, we have 7.5 pounds of synthetic fibers in that program. There are currently 2 fibers that are approved in our specifications, not necessarily all based on performance, but based on mixability, placeability, and finishability. So we are doing another trial on a whole nother set of fiber reinforcement up in Oklahoma City. That's going to occur here in the next couple of months. But we will evaluate those based on how those fibers place and finish up there. If we have a problem, we'll simply burn them off the slab surface. Only issue I've had has been on 2 Amazon projects where I've had problems with what's called the fiducial codes. These are little stickers that they put on the floor slab to guide the robotic units. And if I've got fibers laying up there on the top and the sticker can't reach the concrete, it could impede its adhesion. So that's the only issue. And in which case we just burn them off the floor, but not been a major problem for us. No.
Great, thank you. Okay, last final question from Kevin Grippy. Do your general standards, for instance, vapor retardant, also apply to outdoor applications?
No, never use a vapor retarder outside unless I'm doing something special, like trying to extend my joints, and I'm using the vapor retarder then to lower the linear drag stress out there. So I typically will not use a vapor retarder outside. Now, if I'm trying to force the bleed water up so I can embed a dry shake, like a color shake that I'm using for architectural concrete, that might be a reason to do it. But the vast majority of them don't have vapor retarders there. I would be a little careful, guys, we're running out of good, clean land. And then the land that we are using now for construction, farmers are selling it to us. And what have they been doing out in those fields for the last 40 years? They're throwing chemicals out there. They've been throwing all type of pesticides and different things out there, fertilizer. Those fertilizers have soaked deep into those soils. So if you're doing something architectural outside and you want to limit your risk of any of that potentially coming up through the base, coming up through the concrete in the form of vapor and depositing on your surface in the form of a dry powder, put a 4 mil or 6 mil poly underneath there just for a little added protection. If you're doing it for moisture sensitive floor finishes on interior work, or you're doing it for industrial floor slabs because you're air conditioning the building, 10 mil minimum, 15 mil preferred, especially if you're tailgating.
All right, thanks. That wraps up all the questions. I want to thank Rick Smith. Oh, hang on, one last one from John Wilson. Alternatives to vapor retarder, because we have lots of blistering complaints.
Yeah. So anytime you put a vapor retarder under the floor, you do a couple of things. One is you force 100% of the bleed water up, and that extends the finishing cycle 30 minutes to an hour. And just depending on where you are in our world these days and stuff, but we don't have a concrete that's setting aggressively, and I mean, uniform fashion, then the finishers will get on it too early, and they're prone to making mistakes, especially if you've got high rates of evaporation in the form of wind or low relative humidity. So I'm hearing exactly what he's saying there. And if you've got differential set, for instance, I require that all the concrete has to come from one batch plant or from a dual plant at one location, so that the uniformity in delivery is all the same time across the road. And then it shows up at the job site and it's all, relatively batched at a similar time. When I get differential set out there because I'm supplying from 2 different plants that are separated by 6 miles and 20 miles, that's the kiss of death for a floor finisher. And I don't care how good he is, he's going to fail. So a couple of things I would recommend to you. If you have the vapor retarder there and your set's not there, get the hot water in the concrete, get your cement content bumped up a half a sack to help you. Go in there with your non-chloride accelerators or your code maximum calcium chloride in there. And we've done that for the last 30 years and had very good luck with that. But get the set moving forward. If you're out there waiting for it, your finishers are going to get antsy. And let's face it, floor finishers are not the most patient individuals in the world, especially when they're wanting to be paid. So get out there promptly and get that concrete to set properly so that you don't have that crusting effect on the top.
All right. Thanks, Rick. Great presentation. Hope everybody enjoyed the presentation. Just kind of wrap up here. We'll get you an email with your certificate. We have a presentation scheduled at 1:30 next Thursday with George Siegbrecht on transitioning on concrete curing processes in both the fall and the winter. It should be an entertaining one as well. I hope you enjoyed it. You have Rick's email. If you don't have it, let me know, but he's offered to offer you the PDFs of the presentation. Yep. We also are going to offer an archive. We had a couple hiccups this morning or this afternoon to get everybody started on time. and there are a few people who may not have seen the first couple minutes. So we will have, within a week or two, we will be providing every of your attendees an additional link on our website that will give you the ability to see Rick's presentation again. So thank you for everyone. Appreciate the time you spent with us. We look forward to seeing you next week. Thanks. Bye.
Thanks, Bob.
Thanks, Rick.